In this lesson, we're going to begin to talk about trig equations and their solutions. So you can go ahead and read this if you would like here at the top, but quickly, what's going to be really important here are your special triangles and your quadrantal angles. So from the unit circle, right, knowing our intersection points with our axes as well. So if you would like, you could pause the video and either write them down somewhere where you can use them as a reference the entire time. I will not be drawing them too often. I'll draw them a few times just as a reminder, but we're going to need definitely to know that practice with us. So here's an example, right? To solve this trig equation, sine of x is equal to 1/2. We're solving for the value of x such that the sine of that value is equal to 1/2. And so we have the graph sine of x here, that's in blue. And then we also have the horizontal line there in very faint red of 1/2, okay? And so the idea here is that we're looking for, when we're asking when they're equal to one another, that we're looking for the points of intersection, right? And you might notice, because our sine graph continues on forever in both ways, right? It's a continuous wave left and right, that we're going to have an infinite amount of points of intersection. Well, the first piece says, how do we represent all the solutions? And the solutions that we want to find this time, if you look at this domain we're given, are between 0 and 2 pi. So between 0 and 2 pi, if you look at the x values here, right, our angles and radians, the only ones between 0 and 2 pi would be pi over 6 and 5 pi over 6. So you can think about these in the triangle and where they come from, right? Because you may, hopefully by now, remember from a special triangle that we have a ratio of sides. I used that twice. We have a ratio of sides of 1/2, right? From our 30, 60, 90 triangle, right? And that the sine of pi over 6 is 1/2, right? The other thing we have to take into account, though, is that we're asking for when is sine of x the positive 1/2, and that occurs in two separate quadrants. That occurs in quadrant 1 and quadrant 2. You need to be careful because this is a little bit different than our inverse trig functions, because we're not talking about a function here. We're talking about an equation, right? So we're allowed to have multiple answers. If we extend this, so hypothetically, right, we have our quadrant 1 angle here. So that's the pi over 6 is in quadrant 1. Our quadrant 2 angle was the 5 pi over 6. We would not be in quadrant 3 or quadrant 4 because that would be a negative value of sine, right, for us, but we have positive 1/2. But if we extend this past the restriction of 0 to 2 pi and say, look, well, then we can use this idea of coterminal angles and say, if we said pi over 6 and then added or subtracted any amount of 2 pi's, and we said 5 pi over 6, and added or subtracted, we'll do plus, well, we don't need the minus because we're going to define n as an integer. So we're just going to say plus 2 pi n, and we're going to call n is any integer. In the integers takes place the negatives as well, so that's why we don't need minus. It wouldn't necessarily be wrong if you did plus or minus there, right? But the whole idea is that we can add or subtract a full rotation to get our coterminal angles to get the same thing. Usually we will deal with something like this where we will say between 0 and 2 pi, but if it does not, we need to add in the coterminal piece, our periodic aspect to our graphs, okay? So the idea, you have a couple tips and tricks here. Isolate the function on one side, so isolate the trig function, right? We're going to isolate the trig function on one side, put everything else on the other, and solve. So for this one, all right, I want to maybe subtract 5 sine of x from both sides. I'm also going to add 2, right? So I'm going to put the sine on one side. I'm going to put everything else on the other. And what we're going to get is negative 2 sine x's, right? Because 3 sine x's minus 5 sine x's is negative 2 sine x's is equal to 1. We divide by negative 2, and we get sine of x equals negative 1/2. So it looks very familiar, right? Looks very familiar from our example we just went over. So the first thing that we're going to think about, and so this one I'll draw the triangles to walk through it, is that in our 30, 60, 90 triangle, we have a ratio of 1/2 that occurs. And then we also need to think about ASTC and say, all right, well, sine is negative, since we are negative here, in what two quadrants? That would be in quadrant 3 and quadrant 4. So from the 30, 60, 90 triangle, what this is going to help us with is what our reference angle is going to be, right? Because we know, we just did it, that the sine of pi over 6 right, is 1/2. Well, then the sine of pi over 6 isn't actually our answer because that's in the first quadrant. And we said, well, that would be positive, but we have the negative. So essentially what we're doing is we're trying to figure out in a quadrant 3 angle and then the quadrant 4 angle, which we had just said, right, with a reference angle of pi over 6. All right. So essentially you could think about it as pi and you're going to add the reference angle to get there, which would give us 7 pi over 6 as our answer. Or you could think about this as 2 pi, and we're subtracting it, right? Subtracting our reference angle to go backwards, all right? And that would give us 11 pi over 6. So this helps between 0 and 2 pi, but this just says solve the equation. There's no restriction, right? That doesn't say between 0 and 2 pi, but we've solved it for 0 and 2 pi only. So our answers are going to be this. It's going to be 7 pi over 6, and then we have to say plus 2 pi n. And we have 11 pi over 6 plus 2 pi n. And these would be our two answers. And we should say where n is some integer. Usually we don't deal with this, but because of the fact that we don't have the 0 to 2 pi piece, we need to add the 2 pi n in there as well to take place of the fact that this repeats forever and all the coterminal angles would also work. We also might get a trig equation in quadratic form, so where you're going to see one of our trig functions squared. It's okay to think about this, and this talks about it right here down below, and you can read a little bit more into it, but I'm going to get right into the example. It's okay to take the trig function out of it for a second and put it back in, and so I'll show you what I mean. I'm not going to use x since x is already in here, and that's why they use u up above, so I'll continue on with that trend. But if I want to think about this as 2u squared plus u minus 1 is equal to 0, and I'm going to take cosine of x out and replace it with u, I can do this to factor first. And so whatever form of factoring you have to do to factor this here, right, we can say this is 2u and u. And then you can try all your combinations of the factors of -1, but what you're going to end up with is 2u minus 1 and u plus 1, right? You could even go further, I guess pun intended. You can even go further here and solve both these for 0, and you're going to get that u is equal to 1/2 and u is equal to -1. So you just have to remember, all right, we're not solving for u, we're solving for what u was representative of, and we replaced it to make it a little bit easier looking algebraically. This is really the cosine of x, so we're looking for when is the cosine of x equal to 1/2, and when is the cosine of x equal to -1. And look, we're just solving for between 0 and 2 pi, so we don't need to worry about adding that 2 pi n at the end of our answers, okay? So the 1/2 comes from that same triangle. We can even scroll back up and look at the 1/2, right? So the cosine of which of these angles is 1/2, and that would be pi over 3, okay? So I'm going to start there, and it may even be one of our answers, but I'm going to say our reference angle off our special triangle was pi over 3 for that on the left, and let's deal with this piece on the left first, all right? You could also say with ASTC, what two quadrants am I in? Right? So with ASTC, I am going to be in quadrant 1 because we have a positive 1/2 and cosine's positive there, and in quadrant 4. So this is actually my quadrant 1 angle here, right? So we're good. Pi over 3 is one of our answers. And then our quadrant 4 angle, once again, it would be looking at this like 2 pi and then going backwards by a reference angle, right? So taking 2 pi and subtracting pi over 3, this is going to give us 5 pi over 3. So these are our two angles between 0 and 2 pi that work for the cosine of x is equal to 1/2. We also have to find when is the cosine of x equal to -1. And this comes off our unit circle, right? And so off the unit circle, if we remember, the cosine of x, or the cosine is the x value of the point. So where's the x value equal to -1? That would be at this point here, right? Because that would be the point -1, 0. And that would be at pi, right? So pi would also be one of our answers. So let's write them all together. Usually write them in ascending order. So pi over 3, pi, and 5 pi over 3. I didn't do that in the other ones, but we should. Okay. We'll come back to example 3 together. We could also use different types of factoring. In example 3, you'll see that in class, but we also can use any type of factoring or any factoring method we need in order to solve these. So example 4, using factoring to separate two different trig functions, what we can do first is get everything on one side. So we can subtract 3 tan of x to both sides. Once again, please pay attention to the domain we're solving for here, right? We're trying to solve for these x values, all right? So we don't need to worry about the plus 2 pi n at the end. So when we subtract, we have tan of x sine squared x minus 3 tan of x is equal to 0. And we can think about our different factoring methods, and one of them is a GCF. There's a tangent of x in both of these terms that we can take out. So we can separate that into 1 to get sine squared of x minus 3 is equal to 0. Okay, we can break these apart now that we've factored them and find out when is the tangent of x equal to 0 and when is sine squared of x equal to 3. Or we can even take the square root of both sides here and say this is the sine of x is equal to, and be careful, we need to add in plus or minus. We have radical 3 in here. All right, so we're solving these two. In my mind, I'm thinking, and I'll draw it again here since we didn't have it on this page. Okay, in my mind, I'm thinking this. In the 30, 60, 90 triangle, we had radical 3, so I would just check and make sure, see if this pops up here. All right. Then we also have tangent of x is equal to 0. 0 only came off of our triangle, our unit circle, and we know that tangent of any angle on the unit circle is y over x. So essentially, we're really looking for when is y 0, right? So let's start with tangent of x is equal to 0. When is the y value 0? That would be at these 2 points here, right? That's at 1, 0, because that's 0 divided by 1, and that's at negative 1, 0. So that's at 0, pi. And we don't need to include 2 pi because there's no or equals to on our inequality up here that restricts our domain. So at 0 and pi, those would be our two answers for when tangent of x is equal to 0. All right. Then we need to think about this. Sine of x is equal to plus or minus radical 3. Well, that actually doesn't occur on our special triangle because that would mean that our hypotenuse is 1, which it is not. That would also mean that our numerator is greater than our denominator, which can't be. This is actually out of our range. So this here will not work for us because we never get this ratio from a special triangle. This is also greater than 1, which we can't have, right? Our sine graph, if you think about the wave, the y value cannot go above 1. We hit 1 turn, go down to negative 1 turn, and so forth, right, throughout that whole wave. So this actually does not occur. So our only answers here are 0 and pi. We can even use some of our trig identities to solve. So generally, we're going to only want to deal with one trig function. We just did an example. We dealt with 2 so that a GCF was nice and simple for us. If a GCF isn't nice and simple, we're going to have to use an identity. And one of our really popular identities is the fact that sine squared plus cosine squared is equal to 1. We have our Pythagorean identity here. We're going to want to try to get rid of this here, right? Because sine of x in the middle, that 3 sine of x, that has nothing we can do with it. But what we can do is solve our Pythagorean identity by subtracting sine squared from both sides and get that cosine's 1 minus sine squared, or cosine squared is 1 minus sine squared. And we can use a little bit of substitution and say, well, then, since we know what cosine is equal to, we can use our Pythagorean identity and substitute. So the 2's still here, 1 minus sine squared x in for that. We can use some distribution, and when I use distribution, I'm also going to reorder here. Negative 2 sine squared of x, so I'm just going to write it in standard form, plus 3 sine of x plus 2 is equal to 0. Personally, I prefer to deal with positive quadratic terms or squared terms, so I'm going to divide, or you can think about it as multiplying both sides by negative 1 to flip the sign. So 2 sine squared x minus 3 sine x, so everything just flips signs, minus 2 is equal to 0. And then we have to factor. You could even do what we've done before and replace sine squared or sine of x with u. So you could think about it as 2u squared minus 3u minus 2 is equal to 0 if you want to factor this first, and then we'll work backwards. So 2u and u, and whatever method you want to use to factor this. All right, then we're going to have the minus 2 goes here, the plus 1 goes here. We can split these up. And we're going to get that, well, let's go straight to it. U is equal to negative 1/2, and U is equal to 2. And once again, it's not really U. We just replaced it for the sake of making things easier. This is the sine of x is equal to negative 1/2, and sine of x is equal to 2. Let's talk about it right now. Sine of x can never equal to 2, right? That's out of our range. Our range of the sine graph is negative 1 to 1. Our y values can never go above that, right? So we can't ever hit that point. We've dealt with sine of x is equal to negative 1/2 before, okay? This comes from that reference angle off that special triangle of pi over 6. And ASTC, we're looking for the negative quadrants for sine. That would be quadrants 2 and quadrants 3. So we've done, quadrant 3 and quadrant 4. So in quadrant 3, we said this was 7 pi over 6. And in quadrant 4, we said this was 11 pi over 6. Just make sure in our instructions we were given between 0 and 2 pi. So there are two answers for us here, 7 pi over 6 and 11 pi over 6. Our final one, we're going to go to example 7 that we'll work in. All right, so one, I noticed right away that we're going between 0 and 2 pi, so that's nice for us, right? We don't need to add the 2 pi n at the end. And then we're going to try to solve these. So the issue is, right, some people want to use Pythagorean theorem right away because we have two separate trig functions. We have no GCF, but the issue is neither of these are squared. But we can fix that, and we can fix that by using an algebraic property of squaring both sides, right? As long as we do it to one side, we do it to both. And what we're going to get if we square the left side, please be careful, sine minus cosine quantity squared will give us sine squared minus 2 sine x cosine x plus cosine squared. And 1 squared is just 1. Right? What we can do, you can reorder both sides if you want. Right? So we can reorder both sides, and I'm not going to do it formally, but if you do, you're going to find that you have a sine squared plus cosine squared you can write, right? And that comes from our Pythagorean identity, that sine squared plus cosine squared is equal to 1. So we can write it as 1 minus 2 sine x cosine x is equal to 1. So we always want to get one side equal to 0, so we can subtract 1 from both sides, and you'll notice it cancels on both, and that's negative 2 sine x times cosine x is equal to 0. We can also divide both sides by negative 2, right? Since one side's just equal to 0, that makes our life nice and easy. We're solving for when is sine of x times cosine of x equal to 0. And since it's equal to 0, we can split these up and say, well, that's really when is sine of x equal to 0 and when is cosine of x equal to 0, right? And this comes off of our unit circle as well, all right? It comes off our unit circle, and what we're looking for is when is the y value, right, equal to 0, and when is the x value in the unit circle equal to 0, and that's at all 4 of these points, right? You could even list these out quickly if you want, just so you can double check on which point is which and where you have your zeros. But essentially, when is the y value equal to 0? That's when x is equal to 0. And that's when x is equal to pi. And then when is the cosine of x, or when is the x value equal to 0? That's at pi over 2. And that's at 3 pi over 2. So there's a small issue here, okay? The small issue is this, and please write yourself a note. Since we squared both sides, you may remember from Algebra 2 that we have something called extraneous roots. Extraneous roots can come into play when we square both sides, because what we're doing is getting rid of any negative pieces, right? We're making everything positive. So we need to check our answers for our extraneous roots. Remember, extraneous roots are roots that are given algebraically but don't make sense in the context of the problem. All right. And essentially what would happen is you're going to plug these back into the original, to sine x minus cosine of x is equal to 1. So you're going to plug these all in as x values. And what you're going to find, all right, and for the sake of time, but what you're going to find is that when x is equal to 0 is plugged in, it doesn't work, and 3 pi over 2 does not work. So your only answer should be pi over 2 and pi. All right, so this is just because we have that rule that when we square both sides, our extraneous roots we were taught come into play when we square both sides, that we may need to check our answers just to make sure.